Good day, ladies and gentlemen, and welcome to Unit 1 Solving Multi-Step Equations, day number 10, solving equations with non-integer rational coefficients, otherwise known as fractions. By the end of this lesson, we hope that you will be able to apply appropriate computational algebraic approaches to help solve equations with fractions in them, especially ones where the fraction is represented as the coefficient of one of the variable terms, or multiple variable terms. For today's agenda, I expect you to complete the ed puzzle, which would require you to work along with the video and complete all questions appropriately. That usually suggests that you're going to have to decode any questions, underline, circle, star, or highlight important information, and take notes throughout the video. That may require you to pause the video to write down important details, observations, mathematical facts, rules, and or properties. If you finish early, you may begin the homework and possibly even the Delta Unit 1 assessment. So in question number 1, it's possible if you looked at it in 1a, in a similar way that you may have seen the proportion, or that we did see the proportion equations yesterday, you might suggest to me that a proportion is when two fractions are separated by an equal sign directly equal to one another, and in that instance we're allowed to cross multiply. Since we have a fractional expression in the left-hand side of the equation, you might want to make the whole number 8 a fraction as well by putting it over 1. If you do that, you've created a proportion, two fractions separated by an equal sign. Whenever you're dealing with a proportion, it is true that the cross products are equivalent. So 8 times 3 must be equal to 2x times 1. It's a good idea to cross multiply using parentheses so you don't get lost in your work. So we have 2x times 1 across from one another multiplied together equal to 8 times 3, also across from one another multiplied together. If you were to begin to simplify the expressions within this equation, 8 times 3 is simply 24. And in the expression on the left, 2x times 1, anything times 1 is just itself 2x. But it is a good time to point out that technically we did use the commutative and associative properties of multiplication there. So in simplifying the expression 2x times 1, we could have considered this as twice 1 times x and multiplied the numerical quantities 1 and 2 together first before we multiplied x by x. If we multiplied 2 times 1 first, we would have been using the commutative property of multiplication. The word commute needs to move or change position, and in this instance we would have moved 1 in front of the x, allowing us to multiply 2 times 1 first. It's possible that students would have said, would it have been necessary to put a pair of parentheses around 2 times 1 to assure that we perform that multiplication first? And it's not necessary, but it is allowable. That would be the associative property of multiplication. If your parents say, I don't like who you associate with, they're referring to your group of friends. And we group amounts in mathematics with parentheses. So you could have chosen to use the commutative property to move the multiplication of 1 in front of the multiplication of x. You could have used the associative property to group the multiplication of the numerical quantities. We're only going to be using roughly 5 to 8 properties throughout the entire year, and most of Algebra 2 and much of pre-calculus. So the 5 to 8 mathematical properties or rules that we investigate often are the foundation that we see being used over and over again. As you continue to solve this problem, once you've rewritten the expressions through correct mathematical processes and steps, and they result in the relationship twice x equals 24, you kind of know what the answer is. What number doubled equals 24? And you could undo that multiplication with division and determine that that number must have been 12. Here is a second interpretation or possible process that you might want to solve that equation with. And this is the much more efficient one that I do hope we went over in solving proportion equations, because it is much more powerful, and this is the process that we'll be able to use as the equations get more and more complex. So when you're solving the equation twice some value times 3 equals 8, you could say, too, since we're working with a fraction and fractions have denominators, isn't the real issue here that we would prefer to undo that division at some point? And you could choose to undo that division right away, because you could undo division with multiplication. You could select multiplying both expressions by 3. That's just the multiplicative property of equality. When we multiply, the multiplicative property of equality states that you can multiply an equation by whatever you want, so long as you multiply both expressions equivalently by that amount. You will not change the relationship, you will just make it look different. If you were then to simplify each of the expressions, 8 times 3 would be 24. And in the expression on the left, you're not wrong if you interpret this as 3 over 1 times 2x divided by 3. And you perform numerator times numerator and get 6x, and denominator times denominator and get 3, and tell me that 3 divides into 6x, or 6x is divided into equivalent groups. 3 equivalent groups would result in 2x per group. 3 divides to 6 2 times, and 2 times x is 2x. But it is a good habit to get into to simplify before you multiply. So rather than doing it that way, as you simplify the expression on the left-hand side of this equation, our preference is that you show that 3 in the denominator divides to itself once and divides to 3 into the numerator once as well. And you're left with 1 times 2x divided by 1, which is just 2x, and divided by 1, anything divided by 1 is just itself. Now, I would prefer to show dividing the coefficient of 2 out as multiplying by the reciprocal. So rather than showing it as dividing out the 2, I would prefer to show that we're going to multiply both expressions by a half. We are supposed to know that throughout all of mathematics, division is the same, so dividing by 2 is the same as multiplying by the reciprocal. And the reason that works is the denominator portion means divide. So technically, by multiplying by the reciprocal, we're still saying divide the expressions by 2. 2 divides to itself once in the denominator and into 2x one time as well. And we're left with 1 times x over 1, which is just 1x divided by 1, which is itself. And half of 24 is 12, and 2 divides to itself once and into 24 12 times. And 12 times 1 is 12, and 12 divided by 1 is still 12, because anything divided by 1 is itself. So there are two things I did differently in that presentation. One is I showed you that a more efficient way to solve equations with fractions in them is to immediately undo the division that's presented in a fraction in the denominator right away. Undo division with multiplication. And that's a lot more efficient than cross-multiplying. Cross-multiplying is kind of like a mathematical trick. I don't love it. I use it very infrequently, as I had suggested in yesterday's lesson. I also showed in 1b that it's a good idea to represent dividing out the coefficient as multiplying it out by the reciprocal. Multiplying by the reciprocal forces the division into the denominator, and we end up performing the same step anyway. But what it shows quite clearly is that we're using the multiplicative property of equality here. And the multiplicative property of equality, when we divide out a coefficient, states that you can multiply an equation by whatever you want, so long as you do equally on both sides, and you will not change the value of the relationship, you'll just change the way it looks. Ultimately, making it look like a variable quantity, a letter, is equal to some numerical amount, making it look like the solution that we wanted in the first place. You could check your work here, and it would simply require you saying check that x really is in fact 12, and you would substitute twice 12 into the numerator of the expression on the left, and that should equal 8 according to our original relationship. Twice 12 is 24, and 24 divided by 3 is 8, and 8 equals 8, and therefore we did it correctly. In number 2, ladies and gentlemen, 2a, I'm going to show you a way you might have interpreted this, the process of solving this equation, that would be algebraically correct, but that we don't typically do. In 2a, it wouldn't be wrong to interpret this as a two-step equation and say, teach, when we solve two-step equations, shouldn't we undo order of operations PEMDAS and begin by undoing addition or subtraction first? And you'd be correct. So you could put up a fence. You could choose to undo the addition of 2 to the variable term, 1x divided by 8, and you could choose to subtract 2 from both expressions. Or as I prefer to say, add the inverse. Subtraction is the same as adding the inverse. Any amount plus its inverse just equals 0. So in the expression on the left, when we subtract 2, it simplifies to simply be x divided by 8. In the expression on the right, 5 less 2 is simply 3. You wouldn't be wrong if you interpreted this as a proportion and you said that the whole number quantity 3 could be represented as 3 over 1, and that you could then cross multiply. Not my favorite, I really don't prefer this, in which case you get 1x equals 24. The answer is going to be x equals 24. It's more mathematically powerful to learn the steps that are going to work for the more upper level questions. So it would be my preference that you put up a fence in this relationship, and you immediately recognize that the expression on the left has a fraction, and fractions have denominators, and we're dividing by 8. So it would be a good idea to undo the multiplication of the division of 8 with multiplication. That's going to require you to multiply the entire expression on the left by 8, as well as the expression on the right. Now, typically, I don't show grouping the expression on the left by 8 and then distribute or share that multiplication with all terms. I usually just write it in the first step. I usually just take the originally presented relationship And if I know that I want to multiply the entire expression on the left by 8, I make sure that I multiply all terms, all amounts separated by addition and subtraction signs, by 8. That includes 1x over 8 as well as positive 2 by 8. That would be the result of multiplying the entire expression on the left by 8. I'm making all the values 8 times greater. When you make all the values 8 times greater than the expression on the right, that's simply 5, you get 40. When you make all the values 8 times greater than the expression on the left, 1x divided by 8 times 8, technically that's 8 over 1, and the 8's will divide out, leaving us just with 1x. 8 times 2, when we double it, is 16, and that equals 40. I just then subtract out the 16, and I find out that x equals 24, and I could check my work to make sure I'm correct, but I assure you that you are. Ladies and gentlemen, question number 8. This is a little bit tricky to try and determine the value that when we double it, divide it by 5, subtract 9 will equal negative 19. It's possible to do. We can play with some numbers and eventually figure it out, but I recommend that we take this equation apart. There are 2 ways you could do it. You could undo order of operations PEMDAS, and you could add 9 to both expressions. That would be algebraically correct. Or you could recognize that you're dealing with a fraction right away, and you could choose to undo what a fraction does. And fractions have denominators, and fractions therefore divide. So we could undo the division of 5 by multiplying both expressions by 5. The expression on the left, as well as the entire expression on the right. That includes the fraction and the minus 9. That would be making the right-hand expression 5 times greater. To make the left-hand expression 5 times greater, we've got to do 5 times negative 19, and a positive times a negative is a negative, and if you type into your calculator, it's going to say negative 95. In the expression on the right-hand side, if you were to simplify that expression, it's a good idea to simplify before you multiply. You're not wrong if you say, isn't this 5 over 1, and aren't I doing 5 times 2x and getting 10x? And aren't I multiplying 1 times 5 in the denominator and getting 5? And then shouldn't I divide 5 into 10 and get 2x's? That would be correct, but that's a lot of work. We prefer to simplify before we multiply. So our preference would be to say, why don't we divide the 5 in the denominator into itself once and into the 5 in the numerator once as well. And we're left with 1 times 2x divided by 1, which is just 2x. We're subtracting from that the product of 9 times 5. Product is the result of multiplication, and 9 times 5 is 45. We should then solve a two-step equation, which requires us to go backwards through PEMDAS, and 2 steps always begin with addition. So we're going to add 45 to both expressions to undo the subtraction of 45. And when we do that, we get negative 50 equals twice x, or the question actually asks what number, when you double it, equals negative 50. And if you were to divide by 2 and divide by 2, a negative divided by a positive, one negative sign is going to get us a negative quotient. Quotient is the result of a division expression. And 2 divides to itself once, leaving us 1x. 1x equals negative 25, and we could check our work. If we were to check our work, ladies and gentlemen, I would simply substitute negative 25 in place of x, divided by 5, and subtract 9. The expression on the left is just negative 19. That's easy. And the expression on the right, I may choose to use my calculator to evaluate. There is a fraction key in your calculator. It's actually pretty cool. If you press the alpha button and then the y equals or the f1 function, you get a choice of what type of numbers you'd like to write. And choice 1 is a fraction. And you can substitute in 2 times the quantity, open parenthesis, negative 25 in the numerator. You could scroll into the denominator and put in 5. Then you can scroll to the right out of that relationship, that term, and you can subtract 9. And then you can hit enter to evaluate that expression. And your calculator says negative 19, and your site. Number 10 is not terribly complex. If you were asked to solve this inequality, inequalities are solved just like equations. You wouldn't be wrong if you subtracted 4 from both expressions. That is an effective technique. But eventually you'd have to deal with the 2/3 coefficient of x. And my hope is that when you look at that fraction, you remember that fractions have denominators, and denominators mean divide. And you suggest to undo the division with multiplication. You could do it in the first step, and you can do it in the first step by choosing to multiply the entire expression on the left, by 3. That would undo the multiplication of 3, as well as the expression on the right. Multiplying the expression on the right by 3 is really simple because it's really just 6 times 3, so we're just tripling 6. But when we triple the entire expression on the left, we have to consider that we're not only tripling the variable quantity, we also must triple 4. The multiplicative property of equality says you can multiply an equation by whatever you want, so long as you do it equally on both sides. So when we triple the expression on the left to do it equally triple the expression on the right, we must triple the entire expression, not just the variable term, but also the numerical constant. So as I simplify each of these expressions, the value, or evaluate, the value of the expression on the right is 18. I keep the inequality symbol appropriately as it's written above. 3 times 4 is 12. And now I have to determine what 3 times 2/3 x is. I'm going to suggest to you, as I had a moment ago, that it's super efficient to simplify before you multiply. Divide 3 into itself once in the denominator and once in the numerator. You're left with 1 times 2x, which is simply 2x. Now you can undo order of operations. You're solving a two-step inequality. Two steps begin with addition, typically. You might say subtract 12 from both expressions. I think it's important to know that subtraction is the same as adding the opposite. So I'm going to choose to add negative 12 because any amount plus its additive inverse will equal 0. And I'm left with 2x is greater than or equal to 6. I then would divide both expressions by 2 to divide out the coefficient. I don't want to know the value of 2x's, I want to know the value of just 1. And I'm left with x is greater than or equal to 3. Read it from the variable to the number. Provide the appropriate graph for the relationship. For x to be greater than or equal to 3, I have to identify 3 in a number line. Circle and shade in the circle because technically x can be 3. It can be exactly 3. Or it can be any number greater than 3, so I shade the entire right-hand side of the number line, suggesting that x could be 4, or 5, or 6, ... up to infinity, or any amount in between. Ladies and gentlemen, this was a lesson on solving equations with rational coefficients. Technically what that meant is you were working with fractions, and we're suggesting to you that in addition to many of the appropriate techniques you've learned in years past, that it's not a bad idea to understand that you could use the multiplicative property of equality to clear the denominator or undo the division that's happening in the denominator throughout the relationship. So long as you multiply both expressions by the same amount, you'll be keeping the relationship equivalent. You'll just make it look different, and you'll be able to divide out the denominator and no longer have to solve an equation with fractions in it, which is much more efficient for most students. Good luck, and I will see you in class.